The travel time index is the ratio of the peak period travel time to the travel time at a free flow condition. So we can see that the big cities like Beijing and Shanghai have suffered a lot from the traffic congestion peak period. And this doesn't only happen in China. In the United States, in 2012, according to TTI, a typical commuter will waste 52 hours annually in their commute, which is more than 2 days during 1 year, and the congestion cost is more than $1,000, which is higher than 2 weeks' salary of an average American's income. And this problem doesn't only happen in China and US. Almost all the major cities around the world have suffered lost time, disrupted schedules, wasted fuel and air pollution, and more from congestion problem. And a well-known solution to the congestion problem is congestion pricing, which includes continuous tolls and step tolls. The continuous tolls allow the toll rates to change continuously over time. However, this toll scheme has a lot of political issues, so that the most implemented toll schemes are step tolls. In a step toll, they first determine some toll periods, and the toll rates are constant within each toll period, but they change the toll rates across the toll period. Yet, although the most implemented congestion toll schemes are step toll schemes, the analytical studies on step toll schemes remain limited. Only a handful of papers studied the problem under very heavily restricted user heterogeneity. Here, by user heterogeneity, we mean the user heterogeneity in values of time and schedule punctuality. So most existing studies do not allow the values of time and schedule punctuality to vary freely. However, from previous studies, the user heterogeneity may substantially affect the step toll design and also the welfare effect. Hence, in our study, we try to develop a tool that solves the design problem of the step toll scheme under general user heterogeneity. One thing to note here is that our general user heterogeneity does not include the user heterogeneity in desired arrival time. However, it's fairly order to accommodate the user heterogeneity in desired arrival time. So here we are trying to first formulate the multi-step toll design problem under general user heterogeneity, and then we propose efficient solution methods. After that, we conduct numerical experiments to gain insights of the optimal step toll designs. So to start with, we assume that there is only one OD pair and one link linking the residential area and the business district of the city. A fixed number of users commute during morning rush hour, and they share the same desired arrival time. But the bottleneck there is a bottleneck in a route. They have to queue before the bottleneck to enter the city. Each user now has a unique set of value of time, which is alpha, and schedule punctuality, which is beta for early arrivals, and gamma for late arrivals. We try to minimize the total social cost, which is the total user cost minus the revenue from tolling, to design the optimal step code scheme. Before we start to formulate the optimal design problem, we have to first consider the step code equilibrium. So here we have a simple example which has user classes, blue, red, and yellow, and also a two toad periods, early toad period and late toad period. And there are two untold periods, the early untold period, late untold period. And we consider any one of these periods. Here, for example, we consider early toad period. Within that toad period, for every class, for every user class, under user heterogeneity, in a user equilibrium, they have to have the same user cost, which is the total travel delay plus the schedule plus the toll rate. Here, the total cost is measured by the units of the travel delay. So for each class I and each arrival window j, we have a line, a straight line, which is the isocost curve. So that's how we enforce the user equilibrium within each window. After that, we have to consider how these users balance themselves to across each time period and among each class to get to the user equilibrium. So in UE, all users in one user class must have the same cost. This is how they balance themselves across the arrival windows within each class. And also, the commuters within different user class will use the travel delay, which is the y-axis, to bid for specific arrival time slots, which is the points on the x-axis. So the class that will pay higher price, which is higher travel delay, will get that time slot. Hence, as a result, the upper envelope forms the user equilibrium. Here in this example, it's blue, yellow in untold arrival, early untold arrival window, and blue, red, yellow in early told window, yellow, red, blue in told late window, and all three classes in untold late window. However, this may be quite difficult to solve if we consider this problem still as a dynamic traffic assignment problem like this. So we try to transform this dynamic traffic assignment problem into a static traffic assignment problem. So here we treat each predefined arrival window as a link, linking the origin and destination, where the origin is the residential area and this destination is the business district. And links without the there are capacity constraints for links representing whole windows because they have finite length of time. So classes will balance their costs to meet the demands. Remember that we already have the isocost curves, which are the cost functions of each user class on each link. However, this simple equivalent static traffic assignment network does not show the relationship between all the classes. There are 3 classes, blue, yellow, and red, using the same network. So we consider each user class as a layer on the network. They share the same links and share the same link capacities. So the blue, yellow, red, and yellow will all use the early arrival window, which are these 3 links. And for the other 3 links, it's the same. So each OD pair now represents a user class. So using this equivalent static assignment network, we've already transformed the dynamic traffic assignment problem into a static traffic assignment problem. Then we write out the user cost without capacity constraint correlated penalty in a form of flows, which still contains the first part is the travel delay, and this is the schedule punctuality, and this is the toll rates. And we can write out the flow conservation constraints and non-activity constraints, capacity constraints for those toll periods, and dynamic user equilibrium conditions. With those written out, we can formulate this problem into a VIP problem. So by solving this VIP problem, we can solve the step toll equilibrium for any given toll parameters. So now it's straightforward for us to formulate the optimal toll design problem as a bi-level MPEC formulation. In the upper level, we try to minimize the total social cost, which is the total user costs minus the toll revenue, by changing the toll parameters. And in the lower level, we try to solve the user equilibrium for any given toll parameters. However, this it may be hard to solve this problem, and we may not guarantee a solution. So we try to develop a method that is both efficient and will also give us an exact solution. To do this, we first look at the lower level. Lower level where we try to get the flows and costs as the basic functions of toll parameters. And then by doing so, we will plug in the flows here and the user costs here into the upper level. Then we can get the problem, transform the bi-level problem into a single level problem. And we can also get an exact solution. So the core idea of the methods are first cut the upper level problem into small problems, and then write out the flows and costs as the function of code design parameters explicitly. And then by plugging in them into the upper level problem, we try to transform the bi-level problems into single level problems. So the criteria to cut the upper level problem is the so-called class membership set realization, CMSR. The CMSR is the existence of the user classes within each arrival window. So for this region, there are two different points. Their lower level user equilibrium are different, slightly different. However, the user's existence are the same. It's the idle time and yellow and blue in the early uncode window, idle time blue, yellow in early code window, yellow blue in late code window, and yellow blue idle time in late uncode window. It's the same for the. So here we use the extended equivalent network to illustrate the CMSR. So the solid lines means that user class will use the link, and the dashed lines means the user class will not use the link. So idle time blue use the first window, all three use the second one, yellow and blue use the third one, and all three use the last one. So is the class membership set realization a good criteria to cut the upper level into small subproblems? The answer is yes. The CMSR's feasible sets are all convex sets with explicit linear boundaries. And also, each user equilibrium can only belong to one and only one of the CMSR. So the intersection of any two of the CMSRs is empty. And the union of all the CMSRs is the universe of the problem. And since the total possible combinations of existence patterns are the same, are finite, the total number of CMSRs is finite. So CMSR is a good way to divide the problem into subproblems. Now the problem becomes how to write out the flows and costs as the explicit functions of the code parameters for any given CMSR. So to do this, we first write out the isocost curves equations for each user class in each arrival window. They are straight lines, and we know the slope, and we know the intersect of them. They are linear combinations of user costs and code parameters. Then we calculate the x coordinates of the intersects here, here, and here of the user cost and of the isocost curves. They are also linear combinations of user costs and code parameters. Hence, those after getting those x coordinates, we take the difference of each of them. So they are the flows of the corresponding user class. So this length is occupied by the user class U1. So the flow of U1 in this arrival window is this. This is also a linear combination of user costs and total parameters. Now we know the user demand of all the user classes. So by adding all the flows of one user class across all the arrival windows, we can get the demand. So now we can get one equation for each user class, which on the left-hand side is the user demand, which we know is a number, and on the right-hand side is a linear combination of user costs and total parameters. And we have n classes, so we have n linear equations. Now we've set up an n-dimensional linear equation system to solve the user costs as the linear combination of parameters. Then, by plugging in the user cost here, we can get the difference, which is the flows, also as the linear combination of total parameters. Therefore, by doing this, for any given CMSR, we can get the flows and user costs written explicitly as linear combinations of stepful design parameters. And hence, the subproblems becomes a single-level quadratic program because the upper-level objective function is a quadratic program, and the flow and the costs are just linear combinations of the total parameters. So now a very straightforward way to develop an algorithm is to just enumerate all the possible CMSRs to solve all the subproblems, and we can get the exact solution for the problem, the design problem. So this method guarantees us to find the global optimal solution because it's just enumerate all possible CMSRs, and for each CMSR we can find that solution. However, since the number of CMSRs will increase exponentially with the number of classes and number of poles, so it's impractical for problems to do this method. So we have to find a more efficient way to solve the problem. We first consider the type of the solutions within each CMSR. There are only two types of solutions. The first one type is the solution is within the CMSR's feasible set, which means it's already a local optimum. The second type is the solution is on the boundary of the CMSR. Since the value of the objective function on the upper level is continuous, for this type of solution, it's either the local optimum, or we can find a better solution to go across the boundary to CMSR 6. So in the method, we use the multipliers to each quadratic program to guide us, to find the next CMSR to search. So the criteria is as follows. If all multipliers corresponding to the boundaries are zeros, then it's the type 1. So a local optimum has been found. We stop. Otherwise, for every arrival window, we choose to cross the boundary associated with the multiplier that has the largest absolute value to search the next CMSR. And also, if there is a cyclic searching path occurs, that means the local optimum is on the boundary of all the cyclic CMSRs. So this method works very well in our numerical experiments. Here we first show a two-class with a single-step example. For this small example, we can know that the total possible CMSRs is larger than 700. However, the efficient solution method use around 7 iterations to find the optimal solution. So we first start with a CMSR 1, and it goes through the path, and here is an ending CMSR circle. And if we start even with a CMSR that's infeasible, which means that there is no step-pole scheme that can lead to a user equilibrium that lies in CMSR2, it still will very fastly lead us to this ending CMSR circle, so we can find the optimal solution. Here we consider the circle here and now. The real classes, the yellow and red classes, their existence does not change here. They are the same, you can see. However, which means the idle time for the periods just enumerated all possibilities here. This means that the solution is on the boundary of these 4 CMSRs, and the property of this solution is that there is no idle time hold periods, and also the first commuter during early told arrival window and the last commuter during the late arrival window will have zero travel delay. This is a property that's confirmed by all the previous studies and our study. And then we try to find out the impact of the design flexibility. For the first example, we don't allow the toll rate to change among the early in the second one, we relax this condition, so we allow the toll rate to change from early arrival window and to the late arrival window. So the total social cost decreases as expected, and also the method still performs very well here with only around 7 number of iterations, and also even from infeasible CMSR, it can get us the right solution. Then we try to do an example with more user heterogeneity, and for this problem, using different starting points, different starting CMSRs, we can find 3 local optimal step post schemes. The first one and the second one are looks quite the same. It's just the early total periods changed a little. However, the third one is a total scheme that has a significant lower total price and higher total length. However, all the 3 optimal step post schemes give us similar welfare here, or similar total social cost. So here is the visualized plots for those 3 total schemes. We can see that from total scheme 2 to total scheme 1, the green plus are ruled out of the early total period. Though in total 2 scheme, the green one it's just very small in here. And from total scheme 2 to total scheme 3, the red one, the red class, are ruled out of the untold period. And here the property still applies. There is no idle time within each total windows, and the first commuter and the last commuter during the total windows suffer no travel delay. So our main findings are the optimal total design has properties. The first one is no wasted time within total windows. And the second is no queuing delay for the first and last commuter in early late total. And there are multiple local optima. They are different in design parameters and they are different in CMSR, but they are similar in overall efficiency and welfare effects. And our methods converges fast, and it's also insensitive to the starting CMSR. However, we still need some large-scale experiments to verify this. So our contribute in this study is to provide a tool to analyze the effect of user heterogeneity on step-post design, and also to provide a new perspective to solve this kind of more intermediate problems. So thank you for your attention. Any questions?
Thank you, Mr. Chen. I guess for the audience, you can unmute yourself, or you can start to type your questions from the chat box. It's a great presentation and very solid work. There's a lot of issues in it. Okay, so Hongyu, I may just start something while others are still composing their questions. So I see you use the linear model to represent the isocost curve. Um, I just wonder, I don't do too much tooling work, so just out of curiosity, I wonder, could that be nonlinear, or if that is nonlinear, how would that gonna be? Uh, how would that impact your work? Or
you mean affect the solution or affect our method?
yeah, would your method be general enough to incorporate nonlinear isocost curves? I think
So if there,
yeah, you'll still find an envelope, even if this is nonlinear. But would there be any significant impact to your methodology? Or
so the core part of this method, the solution method, is to write out the float and the cost of as the explicit functions of the toe parameters. So if these functions become nonlinear, it will be much harder get the to um, get their intersect to get their intersections in the second step. But if they're the form of the nonlinear function are simple, it, it, it still works. But it's just too if it's just too complicated, it may be too hard for us to solve the problem, because in step 4 we have to solve an n-dimensional. Now it's nonlinear equation system. It's harder to solve.
yeah, can you just approximate any not too weird nonlinear function with a piecewise linear function? So that this way you may increase your dimensionality a little bit, but
If it's linear, it's still solvable. It will be still solvable, but
right.
But in the method, we have to enumerate which part of the piecewise work
Yeah.
is in the equation.
Yeah. So yeah, great. I think it'll definitely increase the complexity of this methodology. But I feel like my first feel is this method might be able to definitely capture some of those nonlinear functions as well. So if the forms are not too extreme, and you just need to either use piecewise linear approximation, or if the nonlinear functions are simple, and you can analytically calculate those intersections, and when you solve and if the and also it depends on the convexity of the linear functions. The convexities of the nonlinear functions might affect your step 4. Yeah, so anyway, I think this is great work. I'm just thinking, whether it could be extended to address more general cases. It's great, and I believe it has a great potential to that. So thank you. Is there any other questions? Okay, so So, Hongyu, can you send me your presentation slides so I can post it online? Would that be convenient for you?
Sure.
Yeah, you can send me to afterwards, and I believe it has your contact information, right? So, and so if all of you, so if you don't have immediate questions, so I'll just post this video and the slides that Hongyu and send to me later online. You can access all the information, including the previous webinars, videos, and slides from our online Google document. So, and if you find further questions you want to uh, contact the Hongyu, and you please feel free to entertain these questions offline. With this, I will thank all of you for attending this webinar, and especially I thank Hongyu for his great presentation and his contribution to this webinar series. Next week, we're going to have a TRP conference, so we want to have a webinar next month. So the next webinar will be 2 weeks from now, and with this, I wish you a happy new year and see you in 2 weeks.